Welcome to Data Design with Mockup. This is episode 17, and today we are going on a deep dive into something that is honestly just wild to think about. We're tearing apart the mechanics of artificial sight.
Oh, it's a fascinating topic.
Right, because, think about it. When you wake up and you open your eyes, you don't even think about the process of seeing. You just look at your nightstand, and your brain instantly registers the alarm clock, the coffee mug, and, the cat preparing to swat the mug onto the floor.
Yeah, that classic morning panic.
Exactly. But it's this instantaneous biological magic. Millions of years of evolution have just honed your brain to give you perfect spatial context in a fraction of a second. But if you take a supercomputer, right, and point a 4K camera at that exact same morning scene, it doesn't actually see a cat.
No, not at all. It doesn't see a mug either.
Right. It just sees a massive, completely contextless grid of numbers. Just a sea of millions of pixels, where each one has a numerical value for red, green, and blue.
And that right there is the fundamental problem of computer vision. I mean, biological sight is all about understanding context automatically. We just get it. But machine sight, it starts with absolute blindness to context.
Complete blindness.
Yeah. To a machine, a cat is nothing more than basically a localized mathematical variation in pixel intensity.
Okay, let's unpack this.
Okay.
Because to cross that gap, to teach a computer to actually see and understand our physical world, we have to completely rebuild sight from the ground up using math.
Yeah, exactly.
And we all know artificial intelligence requires massive amounts of data.
Yeah.
But the sheer logistical nightmare of transitioning from a machine that just sees numbers to a machine that can identify a dog or a tumor or a pedestrian, it's staggering.
Well, it requires an entirely different scale of instruction than human learning. Think about a toddler. A toddler needs to see maybe 3 or 4 examples of a dog before their brain extrapolates the underlying concept, right?
Yeah, they just point and say, dog.
Exactly. And then they can suddenly identify a Great Dane or a Chihuahua as a dog, even if they've never seen that specific breed before. But a machine needs millions of meticulously annotated examples.
Millions.
Yeah.
Just to get to the level of a toddler.
Right. You're forcing the algorithm to find the underlying mathematical patterns in those pixel grids that actually correlate to the human concept of dog.
So the architecture driving this, the real heavy lifter in modern computer vision, is the Convolutional Neural Network, or CNN, right? We hear that acronym constantly.
Oh, everywhere. It's the backbone of all of this.
But looking under the hood at how the perceptron, the convolutional, and the pooling layers actually interact is fascinating. It's basically a highly structured, automated assembly line for dismantling reality.
That is a great way to put it.
Because the convolutional layers, they aren't looking at a dog. They're applying mathematical filters, like literally sliding a matrix of numbers across the image to find raw geometry.
Right. They're looking for a sharp contrast between dark and light pixels that indicates, say, a horizontal edge.
Wow. So it's just hunting for edges.
Yeah, and that sliding matrix is the perfect way to visualize it. Think of the convolutional layers as thousands of distinct flashlights scanning across that grid of pixels.
Thousands of flashlights. Okay.
Yeah, so one flashlight is tuned to only illuminate vertical lines. Another only reacts to curves. Another reacts to specific color gradients.
So they're extracting these basic features without any human actually telling them what an edge or a curve looks like.
Exactly. But here's the catch. If you just extract every single edge in a high-resolution photo, you end up with an overwhelming amount of data.
Oh, I bet. Just a massive wall of noise.
Yeah, the computer would just choke on the processing requirements.
Which is where the pooling layers come in, right?
You got it.
Because their entire job is ruthless simplification. If the convolutional layer finds a specific texture or edge, the pooling layer just shrinks that section of the image down.
It downsamples the data.
Right. It might look at a tiny 2x2 grid of pixels, find the most dominant feature in that square, and just discard the rest.
And doing that creates what we call spatial invariance.
Spatial invariance. Okay, what does that actually mean?
So by constantly shrinking the data and keeping only the most prominent features, the network learns to recognize, say, the curve of a dog's ear, regardless of whether that ear is in the top left corner of the photo or the bottom right.
Oh, I see. The exact pixel coordinates stop mattering.
Exactly. The geometric pattern itself becomes the focus.
So after you loop through dozens of these layers, extracting edges, shrinking data, finding shapes, shrinking it again, you finally hit the perceptron, or the fully connected layers.
Like the final stage.
And this is where the network takes all those abstract geometric features, flattens them out into a massive list, and essentially holds a vote.
Holds a vote. That's exactly how it works.
The network is basically saying, okay, I have a high probability of a curved edge here, a specific texture here, and a color gradient here. So based on my training, this combination votes overwhelmingly for dog.
Yeah, and the precision of that voting process is exactly why we utilize multi-layered deep learning rather than traditional guided machine learning.
Okay, wait, I was actually going to ask about that. Because why do we need all this complex deep learning? Why not just use standard machine learning?
Well, guided machine learning is where human engineers manually define the features the computer should look for, like simple edge detection or basic 3D modeling. And
Right.
that is highly effective and computationally cheap. We use it all the time for straightforward, highly controlled environments. But deep learning, that is reserved for complex, unstructured realities.
I'd imagine this is why you wouldn't deploy a massive CNN just to sort green apples from red apples on a well-lit, predictable conveyor belt, right?
Oh, definitely not. You just use standard machine learning for that.
But you absolutely need deep learning for something chaotic and high stakes. Like, say, an industrial robot needing to instantly distinguish between a sheet of metal and a worker's hand under flickering factory lights.
The factory floor is the perfect example because the lighting changes every hour, right? The worker might be wearing a different colored glove. There are random shadows, sudden movements.
So a hand-engineered algorithm would just break down in that chaos.
Completely. But deep learning thrives in it because the CNN has autonomously learned thousands of variations of what a human hand looks like under different conditions. It adapts to the noise.
So what does this all mean for the bigger picture? Because these networks are autonomously extracting features from raw pixels, they aren't just limited to pointing and classifying a single object in a frame, right? The visual toolkit has become incredibly specialized.
It very specialized.
When we look at how this technology parses the world, we see a massive difference between something like object detection and image segmentation. But are all these subcategories really necessary? Doesn't it just complicate things?
This raises an important question, actually, because these distinct types are the secret sauce behind the tools you use every day. Like, object detection doesn't just classify what's in the image, it calculates the specific X and Y coordinates to draw a bounding box around it.
Okay, so a box around the object.
Right. And that distinction is critical for interaction. Think about a self-driving car spotting a pedestrian.
It definitely needs to know exactly where that person is.
Exactly. It uses object detection because it's not enough to just know a pedestrian exists somewhere in the visual field. The car's navigation system needs to know exactly where that pedestrian is relative to the bumper and how fast that bounding box is moving across the frame.
Okay, that makes total sense. But a bounding box is practically useless for something like robotic surgery,
Oh,
right?
completely useless.
Yeah, if an AI is assisting a surgeon in identifying a tumor, you do not want a rough square drawn around the general area. You need image segmentation.
Right, and segmentation discards the box entirely.
Hmm.
It evaluates the image pixel by pixel, determining the exact boundary of the object.
So it creates this precise, contoured mask over the tissue.
Yes. Segmentation classifies every single pixel in the image. It literally decides this pixel is healthy liver tissue, but the pixel immediately adjacent to it is malignant.
Wow.
It's a much heavier computational lift than drawing a bounding box, but it provides that microscopic precision you absolutely need for medical imaging.
Okay, so we've got bounding boxes and pixel-perfect masks. Then you have specialized applications like optical character recognition, or OCR, which tackles an entirely different visual problem.
Yeah, OCR is fascinating.
Because instead of looking for physical objects, OCR is looking for the geometry of language. It examines a scanned document or a photo of a street sign, isolates the distinct shapes of the letters, and compares them against this vast database of typography.
It translates a static image of text into searchable, editable digital data.
Exactly.
OCR is really the quiet engine of the digital economy. It's what allows automated data entry on a global scale.
It saves countless hours of manual labor.
Oh, yeah. When you digitize decades of printed municipal records or automate the processing of millions of invoices, you're relying on OCR to translate the physical geometry of ink on paper into binary code.
So we have essentially given computers a comprehensive toolkit for parsing the visual world: classification, detection, segmentation, OCR. And when you step back and look at how these distinct tools are being deployed at scale, you realize they are solving massive systemic bottlenecks across global industries.
Absolutely.
Like healthcare is undergoing a radical transformation because of this. You look at platforms like IBM's Watson Health, they're using advanced segmentation to analyze MRIs and CT scans. And the goal isn't to replace the human radiologist, right?
No, not at all. The goal is to decouple expertise from human biology.
Oh, I like how you phrase that. Decouple expertise from human biology.
Well, think about it. Human biology is the limiting factor in diagnostics.
Mm.
A radiologist is a highly trained expert, but human eyes suffer from fatigue. The human eye can only distinguish a limited number of grayscale shades. Roughly, maybe 30 to 40 distinct shades of gray.
Wait, really? Only 30 to 40?
Yeah, and an MRI contains thousands of nuanced grayscale values. So when a radiologist is looking at their 100th scan of the day, their biological hardware simply cannot process the microgradients of pixel intensity that might indicate a very early stage anomaly.
But the AI sees every single one of those 65,000 shades of gray with mathematical perfect clarity. And it does not get tired at 4 p.m. on a Friday.
Exactly. It highlights the suspicious pixel clusters and just presents them to the radiologist for review.
So it acts as an exhaustive, tireless second set of eyes, catching the microscopic anomalies that biological vision simply isn't equipped to see.
And what's fascinating here is that we are seeing that exact same principle of superhuman data processing applied to urban infrastructure too.
Oh, like smart cities.
Yes, cities like Singapore are utilizing citywide image recognition networks for traffic management.
Okay, so how does that work?
They feed real-time video from thousands of traffic cameras into deep learning models. And the CNNs are running object detection to count vehicles, calculate speeds, and identify accidents or congestion points instantaneously.
Which brings up a massive challenge, honestly. How do you actually use that much data?
Huh.
I mean, if you have thousands of cameras outputting bounding boxes and vehicle counts every millisecond, raw data is completely useless to a human city planner.
Oh, it's just noise at that point.
Exactly. And this is where the concept of dashboard wireframing and structured visualization becomes critical, which is something we talk about constantly here on Data Design with Mockup.
It's essential.
Right. You have to translate that unstructured pixel data from the physical world into structured data points and then feed that into centralized command dashboards so humans can actually make decisions.
Yeah, because the urban planners aren't looking at raw video feeds. They're looking at heat maps, flow metrics, and predictive models generated by the AI's visual analysis.
So the system uses that structured data to autonomously optimize traffic signal timings across the grid. It effectively acts as an omnipresent traffic controller, managing the entire city's flow to reduce gridlock.
It's the complete digitization of physical movement.
It's incredible. But here's where it gets really interesting for me. The application that truly highlights the sheer speed and precision of this technology is out in the agricultural fields.
Oh, agriculture's changing so
Yeah.
fast.
Farming is one of our oldest human practices, and it is currently being revolutionized by hyper-futuristic computer vision, like this see and spray technology.
That tech is mind-blowing.
It really is. You have these tractors dragging massive chemical booms across fields at like 15 miles per hour. And mounted on those booms are high-resolution cameras running real-time image segmentation.
And just think about the processing requirements for this. As the camera moves over the soil, the CNN has to analyze the plant life passing underneath it in real time.
At 15 miles an hour.
Right. It has to instantly distinguish the pixel boundary of a cash crop leaf from the pixel boundary of a weed leaf. It makes a highly complex classification decision in milliseconds.
And once it identifies the weed, it calculates the trajectory and fires a highly targeted microburst of herbicide exactly onto the leaves of that specific weed, entirely sparing the crop right next to it.
It's pinpoint accuracy.
Thousands of times a minute while moving over uneven terrain. It's just wild.
And the economic and environmental implications are profound, because traditional farming requires broadcast spraying.
Right, just covering the entire field, crops and soil included, in chemicals to ensure the weeds die.
Exactly. But by utilizing real-time visual segmentation, you drastically lower the volume of chemicals deployed. You lower the operational costs for the farmer and dramatically reduce the chemical runoff into the surrounding ecosystem.
And they aren't just using tractors. They're deploying autonomous drones to run visual diagnostics from the sky, too.
Yeah, the drone data is incredible.
A drone equipped with a multispectral camera just flies over a massive farm, And the image recognition software analyzes the color wavelengths reflecting off the crop canopy.
It can detect nutrient deficiencies, localized dehydration, or the early stages of a pest infestation days before a human farmer walking the field would notice the physical symptoms.
It completely shifts agriculture from a reactive industry to a highly precise, proactive one.
And this precision is the common denominator across all these applications we've talked about. What's fascinating here is the elimination of human error. Whether you are inspecting microfractures in aerospace components on an assembly line, or reading the chaotic handwriting on a bank check, or analyzing a crop canopy, the machine provides flawless, instant inspection.
Which pushes us toward the absolute edge of what this technology can handle today. We've talked a lot about static images or controlled video feeds, but the frontier of computer vision relies on processing highly complex, entirely unstructured environments in real time.
Yeah, the real world is messy.
It is. But convolutional neural networks have become so efficient and the underlying silicon hardware so powerful that we can now run these deep learning models at 60 frames per second on the edge.
And that edge processing is the foundational technology enabling autonomous vehicles.
Right. An autonomous vehicle is essentially a massive rolling sensor suite feeding data into a centralized neural network.
Exactly. The cameras are pulling in real-time video of the road, and the CNN is simultaneously running object detection to track other cars and pedestrians, semantic segmentation to understand where the drivable surface of the road ends and the sidewalk begins.
And OCR to read the text on speed limit signs, all at the same time.
All at the same time, making life or death classification decisions at highway speeds.
Because it has to recognize that, say, a plastic bag blowing across the highway is safe to ignore, but a piece of tire tread requires an immediate evasive maneuver.
And the algorithmic complexity required to differentiate those two objects in a fraction of a second under glare or heavy rain is just mind-boggling.
It really is. It requires hardware that can process trillions of operations per second locally within the car without relying on a cloud server connection.
Right, because you can't afford a network lag when you're driving 70 miles an hour.
Exactly. And this same edge processing capability is what will drive the next generation of augmented reality too.
Oh, definitely. To seamlessly overlay digital information onto the physical world, your headset has to constantly map and segment your environment in real time.
So it has to understand the depth and geometry of your living room so a digital object can accurately interact with your physical coffee table.
Yes, exactly.
But okay, this raises a really important tension because there's a massive line between convenience and surveillance.
Oh, absolutely.
How do we, as a society, balance the amazing personalization of retail visual searches or automated photo tagging with the massive privacy risks of facial recognition and real-time surveillance?
Well, if we connect this to the bigger picture, it's a profound ethical dilemma. Because the exact same algorithm that spots a tumor with superhuman precision can theoretically be misused for invasive tracking.
Right. The math doesn't have a moral compass.
Exactly. The algorithm doesn't know if it's counting cars to fix traffic or tracking individuals without their consent. Acknowledging multiple perspectives here, the life-saving benefits versus the very real privacy threats, is the only way to responsibly integrate AI into smart cities and healthcare.
We need serious guardrails.
We do.
Looking back at the evolution we've unpacked today, the trajectory is just incredible. I mean, we started with the immense struggle of teaching a machine to recognize a basic pattern in a grid of numbers. We had to feed algorithms millions of painstakingly annotated images just to build the foundational architecture of artificial sight.
It was a monumental task.
And now we are deploying those networks to optimize the traffic flow of entire nations, to diagnose illnesses long before humans can see the symptoms, and to fly autonomous drones over our food supply. We have successfully externalized the biological miracle of sight.
We have translated the physical world into a language that machines can read, analyze, and act upon instantly.
And as we wrap up this deep dive, I want to leave you with one final, profound application of this technology to mull over. We spend so much time marveling at how computer vision serves industry, right? Optimizing factories and farms.
Right.
But consider what this exact same real-time processing capability means for accessibility. We are entering an era where the camera on a smartphone or a wearable earpiece can serve as literal, real-time eyes for the visually impaired.
That is truly life-changing technology.
Imagine an algorithm running semantic segmentation and object detection as a person walks down a crowded street, instantly narrating the physical world to them. It reads the street signs via OCR, identifies an approaching friend using facial recognition, and warns them of a temporary construction obstacle in their path, all spoken softly into their ear in real time.
It's giving them back spatial context.
Exactly. When you wake up tomorrow and look at your nightstand and your biological hardware effortlessly recognizes the room around you, consider that very soon an artificial mind will be able to whisper that exact same spatial context into the ear of someone living in the dark. That is the true power of artificial sight, its ability to illuminate the world for those who cannot see it. Thank you for joining us on this deep dive. We'll catch you on the next episode of Data Designed with Mockup.